So, dear colleagues, let's continue. We're approaching more and more closer to Atiyah index theorem. So let me remind you a couple of things. So what is a generalized Laplacian? It's differential operator L of second order so it works in the sections of the same vector bundle such that its symbol has very specific form minus calculated at vector psi covector psi is equal to, so it acts like identity multiplied by square of the norm of the covector psi and minus sign. To define norm, we need a Riemannian metric So to calculate norm of cotangent vector, we need to have a scalar product on the vector bundle on the base manifold itself. So what is Dirac-Type operator? Sorry, I forgot to say that this guy is formally self-adjoint. So Dirac-Type operator is operator which takes from sections of one vector bundle to sections of another vector bundle, and it is of first order such that d star d and d star are both generalized Laplacians. In an example, we need to.
It's condition, yes, for general Laplacian to be self-adjoint.
Yes, because you need two conditions. First condition is that it's formally self-adjoint. The second condition that its symbol has this form. You know that you can add to the differential operator summands of lower order, and you will broke by this procedure self-adjointness, but symbol will be preserved. So this is, there are two conditions. An example, very important example. So we consider differential forms. We remember that differential forms are sections of exterior power of cotangent bundle. So this is sections of something, and these also are sections of something. And this operator has formal adjoint d star, which can be written in the form nk plus n plus 1 Hodge star d Hodge star. We checked this on exercises this Friday. Well, I have a bunch of exercises for you immediately. First exercise is as follows. Check that d plus d star, this is very important operator, is self-adjoint, formally self-adjoint, and of Dirac-type. It's not very difficult to check. more or less obvious, nevertheless. It has, people call this operator mentioning several names. Usually people say that this is Hodge-Deram operator because it is used in Hodge decomposition of differential forms in the Deram complex. But don't mind for a while. So now we pass to very important part of definitions. So we have this, so new part of material. So operator L, partial derivative operator of order M from one vector bundle to another vector bundle is called elliptic. If its symbol considered at fixed point x and evaluated on some cotangent vector xi, it is a map. From where? From fiber of one vector bundle to the fiber of the second vector bundle over the same point. This is a linear map. And requirement is that it is elliptic, is an isomorphism for all xi which are not zero. So people usually say that a symbol is an isomorphism outside of zero section, and for any point x of the base manifold M. At least it means that dimensions of these two vector bundles are the same. You have a question? Okay, very good. So this is a definition of an elliptic operator. Some properties, some obvious properties. If L is elliptic, then, as you can guess, its adjoint is elliptic. Why? Because the symbol of this operator is just conjugation of the symbol of this one, plus minus sign, but nevertheless it is more or less, you pass from one linear operator to its conjugate, so it's the same. So if one is invertible, then another one is also invertible. If L1 and L2 are elliptic, and we assume that we can form a composition, then L1, L2 is elliptic if it is defined. Next, this is a very interesting thing, but more or less obvious. So assume that L is elliptic, K is just partial derivative operator, and order of K is smaller than order of L. Then L plus K is elliptic. Why this is true? Because the symbol of this operator is the same as symbol of this operator, because operators of lower order do not contribute to the symbol. Next, please have a look at the symbol of generalized Laplacian. It's non-zero. It's because it's just what this thing is doing on vectors. It's just multiplication by this number. So generalized Laplacian is elliptic. So this is obvious. And next question is more tricky. let us Dirac-type operator is elliptic. The question is why it is elliptic. Can you explain me why Dirac-type operator is elliptic?
Because its symbol kind of square is isomorphism outside non-zero.
Well,
hence the symbol itself cannot be.
I think that it should be more delicate, but more or less obvious. Look here. If you consider this composition and that composition, you see that symbol of composition is composition of symbols. So actually, what it means that if you take this operator and calculate its symbol of D and symbol of D star, this is an invertible operator, because it's Laplacian and its Laplacian is invertible. In this order, so first you take symbol of D star and secondly you take symbol of D. This also is invertible. It means that D is symbol of D is invertible and symbol of D star is invertible. So if you have two linear operators, you do not know size of matrices, but it has inverse on both sides. Sigma D star is invertible and sigma D star sigma D is invertible. You are experienced, and I know that you can construct one-side invertible for rectangular matrix. Okay, so easy consequence from this exercise is that D plus D star is elliptic. Why we are so interested in elliptic operators? We have a bunch of theory which we need to skip due to the lack of time. I like this piece of theory very much. Theory of Sobolev spaces.
Those compositions of symbols are invertible outside of psi equal to 0, right?
Yes, sure. Are invertible outside of zero section. So theory of Sobolev spaces provides us with understanding what sits in the kernel of the differential operator. You know, then you study solutions of differential equations, then usually you more or less quickly, I'm trying to estimate how many weeks people spend then study partial differential equations, then they arrive to the notion of weak solution. So you know there's a strong solution and also there's a weak solution. And after that, you arrive to the theory of Sobolev spaces. So the very simple thing which I want to say that let us denote by kernel of the operator L sections which are smooth sections such that L of sigma is 0. This is what is written here. This is solution of differential equation. Yes? Solution of differential equation. but we look for solutions which are smooth, infinitely time, C infinity smoothness. Well, and at the same moment we will calculate some norms in the space of sections, blah, blah, blah. So actually we speak about L1, L2, and so on. These spaces are related by some inclusions. Well, but we are interested in this thing.
You denote both section and symbol by the same letter.
Sorry? Oh, well. Let us write here S.
We wrote sigma of L and now L of sigma seems...
Okay. We apply before this class, I had a lecture on differential geometry, and I write on the blackboard. I used two letters to denote vector field in random order. So I said them. So we defined vector field, blah blah blah, denoted by vector v, and sometimes I replaced it by Greek letter xi, because usually I write xi for vector field. Okay. So, kernel. These are smooth sections which are solutions for this differential equation. The tricky part is that if L is elliptic, then dimension of kernel is finite. Okay, so let me define index of L, index of, or maybe Fredholm index. Index of the operator L is given by this formula. It's the dimension of its kernel minus dimension of kernel of its formal adjoint. Instead of this number, people usually use dimension of co-kernel of L. So it is smooth sections of E2 quotient by image of L. But you know that this, for infinite dimension spaces, this thing is very, very tricky. Usually people discuss, do we need to take a closure of the image or not? In corresponding spaces, and if they are properly defined, image is closed and this guy is finite dimension vector space. But we will not use it. We just take dimension of kernel of adjoint operator. It is the same if you sit in the if your theory of spaces is well developed. So we skip this thing. We need only this statement, and this definition. So the subject of our lectures finally, not finally, appeared already. So that we speak about index. It's the left part of the formula. We discussed this thing, index. And the next thing which we need to obtain is the right part of the formula. Right part of the Atiyah-Zinger theorem. Let us spend a few time to discuss an example of index. I will erase everything except this guy. What I want to consider an example. Okay, so let us consider. So we want to consider operator which is D. No, I don't want to introduce letter D. D plus D star. The problem is that operator D raises the degree of the form, D star lowers degree of the form. So I will write here this in this way. So omega star is just direct sum of all omegas. Okay. My question: what is the kernel of d plus d star? How one can describe it? In general case, it's difficult question. But we assume M is closed, compact plus no boundary, oriented, and equipped with metric, so it is Riemannian. So it is equipped with metric. In this case, kernel of this guy can be explained in a very, very interesting way. Do you, I believe you heard about Hodge decomposition. Let us define. Kernel of this guy is harmonic forms. Maybe. Who knows definition of harmonic form?
Eigenform for the square of this operator.
Eigenform? I thought it was kernel.
No, eigen is okay, just harmonic, just the square of this form.
So let us consider. So this is a Dirac-Type operator. So there is a Laplacian which corresponds to this guy. But since this thing is self-adjoint, both of them are the same. You can write it in this way. So people usually consider square of this operator. It's a very good operator. Let me expand the brackets. Then you will see d squared, d star d plus d star plus d star squared. These two things are zeros. And the pretty funny thing is that, let me define it by delta. Delta sends omega k to omega k. It preserves the degree because these two summands vanish, and these two things, one raises the degree of the form, another one lowers. So you see it's still here. So harmonic form is just HK is just kernel. Kernel is defined to be kernel of delta, which acts as in omega. This is a definition of harmonic form. What I want to ask you to check a couple of exercises. Okay? We need to do something on Friday. That's why I need to give you exercises. First exercise is very simple. We will use that it is closed and oriented. The exercise is as follows. Omega is harmonic if and only if d omega is 0 and d star of omega is 0. So kernel of this guy is intersection of kernel of the Ram differential and this adjoint operator. If you HK is isomorphic to the Ram cohomology of the manifold M. To check this, we note a very simple thing that since harmonic form is satisfies this equation, we have a projection. Harmonic forms can be mapped to the Ram cohomology because then you send harmonic form to its cohomology class. We want to prove that two things. One thing is to check that if harmonic form is non-zero, then the class is non-zero. So first you need to prove that if omega is differential of theta, then omega is 0. To be more accurate, provided this is a harmonic form. And the second thing, you need to check that inside cohomology class which sits here, there is at least one harmonic form. You just need to spend some time playing with operator D and D star and a metric on differential forms. It's not very difficult. So it's very simple exercise. And actually, maybe you will, it is more convenient to prove the following thing that Hodge-de-Rham decomposition in this form. The space of forms is decomposed in orthogonal direct sum. So to indicate that this sum is orthogonal, I will add here dot. It's not just sum of vector spaces, direct sum. It's just orthogonal direct sum. Differential of omega k minus 1 and d star of omega k plus 1. From my point of view, this exercise and this exercise are more or less the same. So it was advertised for harmonic forms. And now we want to discuss the index of this operator. Index of this operator. Question. Well, look. Yes, one more question. Kernel of is the same as kernel of. Please tell me, is it correct statement or not?
May I ask a question?
Yes.
I don't remember if we discussed scalar product on omega k. It is integral over m of.
Be careful. There are two notions of scalar product. First of all, you imagine what you have. You have a scalar product in all tangent spaces. Then this guy induces scalar product in all cotangent spaces. Then you define scalar product on each exterior power. Yes?
Yes, we can define scalar product
Pointwise, and then you need to integrate.
Yes.
This will be definition of the scalar product with respect to which you define d star, because otherwise d star is not defined. D star is defined for scalar product on sections, and then integrating. Okay. So, question: is it correct or not? Yes, it's correct, because if you consider for differential form, which is harmonic, it sits in dimension k, it sits in the kernel of delta. If you calculate element from this kernel, these two operators hit to two different spaces. So actually, if d plus d star of differential form omega of fixed degree is 0, it means that both operators are 0, because d plus d star works in two different spaces. Well, so this is okay. So then we discuss kernel of this operator is just space of harmonic forms. Gentlemen, no ladies, so gentlemen, tell me please, what is an index? Let me write the index of d which acts on this. So this is a space of sections of some vector bundle. You can calculate it. Oh, sorry, not D. Index of D. Nobody knows what is an index of D because D is not elliptic. But D plus D star is elliptic. Why?
Because it's self-adjoint.
And? Yes, the answer is absolutely correct. Because the index, so what you need to do, you need to take, you calculate dimension of kernels of the operator itself and subtract dimension of kernels of adjoint operator. It coincides with adjoint operator, so you have difference between two same things. This thing is total dimension of cohomology. Minus, no, zero, it's zero. Any self-adjoint operator will give you. You need to ask me why I spend so much time discussing Hodge-de Rham operator. The answer is very simple. Because this is a wrong way to consider source and target for this operator. We need to change it. Let us do the following. Let me remind you that these two things change the degree of the form. So we can restrict this operator to form of even dimension, and then both of them change the parity of the degree. So this guy sends this to odd. Yes? In this case, it's adjoint. For sure, it is given by the same formula, but it's different operator because it works in different directions. So if you consider it's adjoint, it sends odd forms to even forms. Now, I want to ask you about index of this operator. Please, go on. Let me add another exercise. If it is not given, I want to see symbol of D plus D star. It's very, very funny thing. So, dear friends, please, let us calculate the index of this operator. The question is quite simple. What we need to check? Dimension of kernel minus dimension of kernel of adjoint operator. So, from what things kernel of this operator consists?
Consists of forms of even degree which are set to 0 and of odd degree which is
Yes. Kernel of D plus D star, which works from even to odd, is just harmonic forms of even degree. And kernel of its adjoint, which is given by the same formula D plus D star, but it sends odd forms to even forms. It's just harmonic forms of odd degree. So, what can we say about index? Very simple thing. We take sum of h2k minus dimensions of h2k minus 1. What is the name for this quantity? Daniel, what do you think about this? What is the name for this quantity? Yes, it can be written in alternating sum of what? Of dimensions. So harmonic forms are the same as cohomology. The rank cohomology of M. It's exactly what is known by Euler characteristic of the manifold M. So this is the second index we already calculated. First one is 0. So we can think that in this case, Atiyah-Zinger theorem is proved because you take 0 characteristic class on the right-hand side and integrate it over M. So, okay. But in this case, we have something interesting. So we have two different space of sections. So imagine differential operator. Differential operator. You need to solve differential equations, Fredholm alternative, blah, 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 many things related to functional analysis. But suddenly you obtain purely topological characteristic of the manifold. It's Euler characteristic. Very good. I forgot if we already discussed it, but maybe yes, maybe no. But do you remember we calculated Euler class? Euler class. Pfaffian and so on, so on. So if you apply Euler class to tangent vector bundle of M and integrate Euler class over M, you will obtain the same thing. Actually, Atiyah-Zinger theorem should give us exactly this expression, because this is the aim of Atiyah-Zinger theorem. You have some analytical quantity, which is an index of some differential operator. It's a number, and you should represent it as a characteristic number, integral of some cohomology class in some universal way. So this is one of the manifestations of Atiyah-Zinger theorem. Another one as follows. We will split differential forms in different way. So the problem is as follows. The space of differential forms is very big. This operator is self-adjoint on them. And what we did actually, we split the space into even part and odd part. And operator D plus D star interchanges them. So if you will write a matrix for this operator, it has this form. So it sends first summand to second and vice versa. And then you calculate the index only for this corner of the matrix. Quite trivial. But you can consider different decomposition. Let me explain it, and I will give you it as an exercise. But this exercise is very difficult, and I think we will spend not 1 week, maybe a couple of them, to discuss this in details. This is the second important example. This one is the first important example. Second important example is as follows. We need to describe another splitting of omega. We split this guy into differential forms of in different way. For this purpose, we assume that our manifold is the same as written there, but the dimension is 4m. The discussion for splitting, blah, 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 works for every case, but this case is important. What we are doing? we have Hodge star, yes? What happens if we apply Hodge star twice? It sends omega k to itself, but it's not an identity, yes? It is, as far as I remember, something like that. Let us think that everything is complexified. We complexify this. Then we can replace Hodge star by this type of star. It will be given by I to the power k n minus k. And then you can define omega plus as a space of differential forms such star is of eigenvalue 1 and omega plus, and omega minus as space of forms such that star of omega changes the sign. So it's eigenspaces for plus 1 and for minus 1. What you can do? You can check that d plus d star interchanges them again. The question, very simple question, what is an index? So this is an exercise. For those of you who are students of the Department of Mechanics and Mathematics, students, not students of master program. Everyone else, not you. Not you. you. Okay, the question is, I believe you know the answer. I know more or less topic what you are studying with your scientific supervisor. You know the answer. Okay? So I left this as an exercise for 1 week, maybe for 2 weeks. Okay. What we're doing further.
And the whole space of forms is decomposed as the sum because this star operator is an involution.
Yes. Star squared is identity. Actually, in this case, you can say, you can say, okay, it is an eigenvector. This is an eigenvector. We know that sometimes eigenspace is much smaller than root space, but nevertheless, it can be done in the following way. You can see the kernel of what? Of this operator, 1 minus star. The kernel of this guy consists of these things. And this can be defined as a kernel of another operator, 1 plus star. And in this case, you can very easily explain that kernels of these two operators give you decomposition in the space in two subspaces. Because sum of these operators is identity. Oh, okay. Their composition is 0, so no problem to prove that the kernels decompose the whole space into direct sum. No problem. Okay, so you have, please have fun. It's very interesting. But now we need to go further. So we already discussed what is happening in the left-hand side of the Atiyah-Zenger theorem. This is the index of some specific operator. The formula which we will discuss is about index of Dirac-type operator. So we discussed Atiyah-Zenger formula not in general case, for Dirac-type operators. So we need to look at those operators a little bit closer. And I need to make you acquainted with very, very important thing, which is Clifford algebra. Daniel, do you know what is Clifford algebra? Okay, do you know what is Clifford algebra? No, so let me explain you what is a Clifford algebra. For this purpose, we will do some trick. Okay, let us do some trick to see that the Clifford algebra appears in this setting very naturally. We are not introduced it inside this stuff. It appears by itself. So let C be the symbol of our operator D. D is a Dirac-Type operator. Okay. So what we can say about C of xi composed with C of xi? We apply C of xi twice. What can be said about that? This one is symbol of D. And this one is also symbol of D, but I cannot multiply D and D again, yes? Yes, it's minus symbol of D star. So this guy is no, conjugate. Yes, it should be conjugate. So this is minus xi squared identity times identity. Is it correct?
Type operator is of which order of 1?
Sorry, D?
Yes.
Yes, it is of order 1.
Yes, we've had an exercise.
Okay, very good. So this is a correct formula. Next thing which I want to say, so we can consider C of xi as an operator which acts from E to E. From one fiber to the same fiber. And this operator is linear. It's for xi non-zero, it is invertible. And if you take a square of this operator, you obtain minus norm of xi times identity. Very good. Let me ask you, what happens if I consider C of xi plus eta squared? What happens? Since this is operator of order 1, symbol is linear in xi. Yes, because if it were of order 2, it will be quadratic. Of order 3, it will be cubic. But it is of order 1, so it's linear. So actually, what is written here is C of xi plus C of eta squared, and we can write it in this way: C of xi squared, C eta squared. C of xi, C of eta plus C of eta, C of xi. Okay. So minus what can be said about this quantity? What is it?
Something like scalar product.
Yes, exactly. Two scalar products of xi and eta. So this scalar product is calculated in a cotangent vector space over the point x. Okay, so we arrived at some very specific formula. No, sorry, what? No. Sorry. Very, very sorry. I do not know what is written here. I do not know. So this is operator which corresponds to psi. This is an operator which corresponds to eta. Nobody knows what happened. But other part of the expression can be calculated. What is written here? This is two sides of some parallelogram. It's diagonal. So what is the or maybe you can calculate directly what can be said about this scalar product. Xi squared cancels. Eta squared cancels. But cross product.
Doubles scalar product.
Yes, exactly.
Minus double.
Yes. So we arrived at some very interesting relation. So if you take operator which corresponds to cotangent vectors and take this their combination in this form, you obtain the usual scalar product of these two vectors twice with minus. Scalar product is taken in cotangent vector bundle. And this is very, very important relation which forces us to consider the following algebra. Assume we have a vector space V equipped with a scalar product G. Finite dimensional vector space. We can say that it's bilinear form. In general case, it can be degenerate, it can be it can be not positively definite, not negatively definite, maybe. But for us, it is scalar product.
The right-hand side is actually should be actually multiplied by the identity.
Yes, sure. So for us, scalar product in general can be bilinear form. In topological applications, this bilinear form should be non-degenerate. Most interesting part. Then we can construct the following algebra. Clifford algebra defined by vector space and bilinear form G in the following way. You take tensor algebra of the space V and take a quotient by the following two-side ideal. V tensor W plus W tensor V plus two scalar products of V and W. You know what is tensor algebra? Sure. Okay, we can write it. It's infinitely dimensional algebra which consists of one-dimensional vector space. Then we take a direct sum. V plus V to the tensor power 2 plus V to the tensor power 3, blah, blah, blah. It's infinite. It is an object of infinite dimension. But we add here this relation. So if you have element in this tensor product, second power, this one plus this one, there is a relation which says that instead of this combination of two elements in this tensor power, you can consider this element with minus sign in this space. Very good. So what happened here? Symbol of the Dirac-Type operator. C defines an action of what? Of Clifford algebra defined on cotangent space at the point X and the scalar product on what? Where it acts? It acts on fibers of our section over point X. So this is a Clifford algebra defined by a very simple thing. It's finite dimensional vector space and non-degenerate scalar product. No problem. There is a full description of such objects. But this Clifford algebra acts on the fibers of our vector bundles. So we need to understand what are possible actions of Clifford algebras on finite dimensional vector spaces. So let us start the description. Well, to make you more familiar with Clifford algebras, for those who are not yet seen it, okay, let me give you a couple of very simple examples. First,
is there a notion of Clifford of cotangent bundle?
sorry? Clifford bundle of cotangent bundle is available. It will be used. It will be used. Because how to explain it in a simple way? So you pass to local charts.
It's a bundle of algebras.
Yes, it's bundle of algebras. How you construct them? You pass to trivialization, local chart. And this local trivialization, you have direct product of Clifford algebras by neighborhood, by chart and the base. Okay. Then you pass. Then you take change of coordinates, change of trivialization. You have automorphism of Clifford algebra, and they give you complete data to glue them together. So let us consider a very simple example. We take V equal to R, and scalar product will be very simple, one-dimensional vector space. So, no. Much better to pass to coordinates. Much better to pass to coordinates. Non-degenerate scalar product in certain bases can be written in the form, can be represented by the matrix some pluses and some minuses. So corresponding Clifford algebra is usually denoted by this simple symbol, because it does not depend on the choice. So, if you have another presentation of scalar product by this Gram matrix, then you will have different isomorphisms. So nobody cares about that. So a Clifford algebra which correspond to this scalar product has this form. So my question is, what is a Clifford algebra with these numbers? Clifford 1, 0. To understand it in a very, very fast way, we need to understand how can we rewrite this general collection of relations for this algebra. So tensor algebra, in this case, will be free associative algebra with unit generated by E1 blah 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 En, which is EP plus Q, where E is orthonormal basis. Why so? Because these guys generate V, their pairwise products generate this thing, three-time projects generate this one, and so on, so on. And what are the relations? Very simple. If you take EI and multiply it by IJ, it will be minus EJ EI. Why? Because scalar product in this case is 0, so if you interchange the order of these two things, it will change sign. What happens if you take EI squared? There are two different options. First of all, if number I belongs to the first P coordinates, then according to this relation, what you need to do, you need to send this thing to the right-hand side of the equality. So this will be +1 for e smaller than p, not greater than p. And -1, sorry, twice. So minus here and plus here for e greater than p. Okay? The question, what is Clifford 1,0? It has one generator, yes? And what is the relation? Guess who is it? Sure, definitely. It's complex numbers. More tricky question. Clifford.
Okay, it was over C.
Sorry?
It was over C.
What was over C?
V is complex vector space.
Yet not.
If we take Clifford 1,0 of R, not of C.
Yes, it is complex numbers. It has two independent elements, linearly independent elements. 1 and E1. E1 squared is -1. That's complex numbers. More difficult question, who is Clifford 2,0? Now it has two multiplicative generators, E1 and E2. And the relations are a little bit tricky. So E1 squared, E2 squared is -1, and they anti-commute. If you interchange the order, the product changes sign. Guess, who is it? Quaternions. Yes, but in quaternions we have I, J, and K. Where is K? Yes, E1, so yes, it's. Thank you very much. These are quaternions. Unfortunately, Clifford 1,1 and Clifford 0,2 are not so good. They are not complex numbers. They are not quaternions. These are matrices 2 by 2 over R. And if you want, you can construct the isomorphism in a very direct way. You just need to say which matrix corresponds to generators in the Clifford algebra. It's not very difficult, but there are not so many generators and matrices, so it's very more or less simple. It's not very difficult to find matrices which correspond to relations in this algebra. Okay. Oh, so the matrices which satisfy relations of such type. Okay. So let's erase it. I have a very good news for you, that matrices, that Clifford algebras are not very difficult. They are either algebra of matrices over C, over H, or over real numbers, or matrices plus matrices. So depending on numbers, so this can be real numbers, complex numbers, or quaternions, or maybe it is direct sum of these two. So it's not very difficult. So it's more or less familiar object, and it exhibits a kind of 8 periodicity for real case and periodicity 2 for complex case. So for a while I don't want to use classification theorem. Let us discuss it more relaxed way. So so we have time, okay. So let us introduce some notation. We will take about supergraded spaces or S-graded, the same, if it is represented as the sum of two subspaces which are denoted by E plus and E minus. Why we say about the two graded? Because then we have some automorphism. Then it can be represented as a matrix of such form A, B, C, D, and T can be decomposed into sum of two linear operators. T even is represented by matrix A, D, and T odd, its odd part is represented by matrix of such form. What can I say about that? That T even preserves the parity, yes, and T odd reverses the parity. So if you take a vector from E plus, T even send it to E plus. If you take a vector in E plus and apply T odd to this vector, the result will belong to E minus because of the form of these matrices. T itself has no relation to parity of these subspaces because T sends vectors from E1, nobody knows where, because it acts as this part of the matrix, nobody knows where it. So the result does not belong to E1 or E plus or E minus, it's a kind of diagonal there. Okay, so now I want to define so-called super trace of T. As you can guess, the diagonal part of this matrix T appears only in even part of T. T odd does not contribute to the trace. But since this has plus part and minus part, we define it as follows. We take trace of even part restricted to E plus. And we take trace of T even restricted to minus part and take their difference. So this is a notion of supertrace. Well, next question is, what is a super algebra? Let me erase here. Why we need this discussion? Because Clifford algebra is Z2 graded algebra or super algebra, and it's natural to consider super trace inside it. A, which is presented as this form, is S algebra, super algebra, Z2 graded algebra. If we have obvious rules.
May I ask a stupid question?
Okay.
So here it will be trace A minus trace B. Yes.
Trace A minus trace D. D is here. A, B, C, D. We had here A, B, C, D.
У нас trace even.
Yes.
Trace. Там тоже trace even. Там не odd, да?
No. Odd does not contribute to the trace because these elements are outside of diagonal.
I have another question.
Okay.
While is stable under the all change of coordinates. This supertrace is stable over.
I will write the formula and leave it as an exercise.
Or the change is coherent with this.
Yes, yes, yes. So, obviously we have, so that's a part of definition. So it is graded, but multiplication should be compatible with this grading plus, so you know the standard rules, plus by plus gives you plus, blah, blah, blah. If you want, we can, so if you write 0 and 1 instead of plus and minus, then you can write this something like that, that if you take a product of two grading subspaces, it should land to the subspace where grading is sum of these two gradings considered modulo 2. It is the same. If our space E is graded, then space of its endomorphism is also graded. How to represent an operator? We checked as endomorphism here into even part and odd part. We already did it. Every operator can be represented in a unique way as a sum of even part and odd part. So the endomorphisms of graded, well, S graded. So endomorphisms is S algebra, supergraded algebra. So to stress it, we add here a hat. To stress the grading. Otherwise, we will forget about it. Why it is important? Because for supergraded algebras, there is a notion of supercommutator. Those of you who are more or less familiar with physics will be not surprised to see the definition. So if you take so let A plus minus and B plus minus belong to A plus minus. So we have superalgebra A and we have elements of different parity A and B. And I want to give you a definition of supertrace. If you take, oh, not a supertrace, sorry, supercommutator. Supercommutator, in this case, is standard commutator. Let me write it in explicit way. If you take supercommutator with A plus on the first place and B something on the second place, it is given by the same idea that it is standard commutator. There only one formula is left. Which one? Yes, and this is an anti-commutator. If you take a supercommutator of A minus and B minus, it will be A minus B minus plus B minus A minus. The only small difference, only in this place. Supercommutator knows about this sign. It should be minus here. Those of you who are familiar with homological algebra can write one formula for all three formulas. Okay, what is the most famous relation between trace and commutator? That if you calculate trace of the commutator of two elements, it will be 0. But you know that supertrace is something different. Something, you take only part of the matrix, you take one part of trace with plus, another part of trace with minus. So in supergraded case, obviously this formula doesn't hold. But exercise. If you take supertrace of supercommutator, it will be 0. So A and B belong to A, which is S algebra. Which one? Endomorphisms, graded endomorphisms of the graded space. Because we have no trace for abstract algebra, we need to be this algebra to be endomorphisms of some vector space. Okay. Okay. So definition. We have time? Yes, we have some. Definition. What is an S module? Module over, well, so over S algebra A is S graded space and representation. Homomorphism of which form? Which form? So A is sent to graded endomorphisms of E, compatible with parity. Compatible with grading. So in algebra A, you have even elements and odd elements. They should be sent to the elements of corresponding parity, even to even, odd to odd. In this case, you say that you have S module. E is an S module over A. This is exactly what happens in our situation when we considered Dirac-Type operator. So let me finish maybe in 5 minutes. I want to tell you one theorem about dimension of the Clifford algebra. Statement. Real one. It is just 2 to the dimension of V. It's not difficult to prove inequality in one side, that dimension is not greater than 2 to the power of dimension of V, but I want to prove that they are equal. There are several ways to do it, but inside the proof we will construct one very specific map which we need in the future. So let us start. Let us start. Well, I forget to say that Clifford is S algebra, so it's graded. So then I will speak about algebra. This algebra, I will speak about grading also. It is Z2 graded, so it has even elements and odd elements. Proof. To introduce grading here, it's not a very difficult task. Let me say that let me denote it by epsilon. Epsilon is defined on the V itself, and it sends vector v to the vector minus v. It changes sign at the vector v. What I want to say, that first of all, we can define automorphism of tensor algebra. You change sign at every vector you see in the expression. It's still homomorphism, no problem. Epsilon applied to the relation. I want to check that epsilon preserves the ideal of relations. What do you think about that? What happens if I apply epsilon to this expression? This is an element in tensor algebra. What it did? It changes sign at v and at w. So the product is not changed. It changes sign at w and v, so the product is not changed. Here, okay, you can change, so it is a number. There is no reason to change the sign. So epsilon preserves the ideal. Hence we have epsilon.
No, there is the reason to change sign, but it's not changed since G is bilinear.
No.
We change sign.
We change sign here, and but not here because it's number. It's just number.
But we should probably define epsilon on numbers.
Epsilon numbers doesn't act. Epsilon on number is identity. Is number. Okay, epsilon of 5 is just 5. It's just. So epsilon defines automorphism of Clifford algebra. But you know that epsilon square is identity, so we can split Clifford into two eigenspaces for epsilon and say that Clifford plus is given by which formula? It's kernel of 1 minus epsilon, and Clifford minus of Vg is kernel of 1 plus epsilon. How to prove that the product of these guys is compatible with this decomposition? Very simple. Epsilon is a homomorphism of algebras. Yes? So if you take eigenspace for 1, this one is eigenspace for minus 1. So from this, it follows that plus minus on cl is Z2 grading. Okay. We already spoke about bases, so let me consider E1 blah 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 En, where n is dimension of V over reals. This one is orthonormal basis for V. Then we have relations that EI squared is plus minus 1. I don't care what happens to the sign, but I know that EI ij is minus EJ EI if EI and if indices are different. This gives me the possibility to do the following. If I have a monomial, the product of this of arbitrary number of these guys, by this relation, I can put indices in increasing order. And then I see two indexes which are repeating. I can cancel them by this equality. Then any x in Clifford algebra is a linear combination of elements of such form EI blah 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 EIN, where indices are strictly increasing. Ik This is no greater than 1, this is no greater than 1, and 1. My question is, how many symbols of such type you can find? Hmm? Yes, very stupid question, I'm very sorry. Number of these elements is 2n. From this it follows that dimension of Clifford algebra is not greater than 2 to the power of n, as I promised. It's a very simple statement, because you can take basis and v and write elements, finite number of elements, exactly this number, 2 to the power of n, such that any element in Clifford algebra can be represented as a linear combination of such elements. What we need to prove? That these elements are linearly independent. Otherwise, if they are linearly independent, then this dimension will be strictly less than 2n. We can do it by different tricks, by defining filtration in Clifford algebra, blah, 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 but I want to show you one very specific trick which is useful for us in the future. For any vector v which belongs to the vector space V, define C of V, an element which is endomorphism of exterior algebra defined by vector space V. In a very simple way. So this guy applied to element from here is given by the following formula. It contains two summands. Exterior product with V, and then minus well, I need to explain what is written here. E, its internal product. Dual to the exterior product is a so-called internal product. And V star is a E is an inner product. You are familiar with this thing. Then you substitute to the long differential form given vector in the first place, inner product. This operation decreases the degree of differential form. But now we are not speaking about differential forms, it's about vector space and its exterior power. So we cannot substitute into this element of this space itself. We can substitute the element of a dual space. So V star is an element of dual space G dual to V. It means that V star of any W is a scalar product of V with double. Oh. So let me write that this way. So this is a covector which is defined by this formula. So this is a formula for C.
So the last term is just V and G of V and W, no?
No, W is a long product. Actually you apply scalar product to each term there, take sum with corresponding signs, blah, blah, blah. There is exact formula for this. So exercise. Calculate what happens if you take a square of this guy. It will be minus V squared identity. I guess you already saw this formula. It's symbol of the Dirac-Type operator, or symbol of generalized Laplacian. Very good. So from this it follows we have a morphism of algebras. We have as graded morphism of what? Clifford algebra to the endomorphisms of exterior power of V. But since I mentioned that it is as graded, I add here hat, just to stress that we consider endomorphism of this thing as graded. Very good. So any element here defines an endomorphism of exterior algebra. So we finish the proof by a very simple trick. Let us calculate. Let us calculate so this guy's evaluation of element of Clifford algebra. What is written here? You just S of Clifford say A, is just evaluation of C of A on 1. So this guy belongs to lambda V. So we take endomorphism and evaluate it on on element 1. Now, very simple thing. How to prove? How to check that products E1, blah, 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 EEK are linearly independent in Clifford VG. And 1 for sure, and 1. How to check? We evaluate sigma on them. Sigma of EIK, blah, 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 EIK is equal to C of EI1, blah, 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 C of EIK applied to 1. The nice thing about this is as follows. It's difficult to understand. Okay, I gave the definition of this summand, but it's obviously not very, very simple. We need to calculate something. We finish in a moment. But what do you think? Is it possible to take a contraction of 1 with dual vector to E1? EIK. No, there are nothing to contract. So second does not appear. So this is just CEI1, blah, 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 C of EIK minus 1, EIK. Next, we take this guy. First of all, we take exterior product, and then we're trying to contract. How you will contract two orthogonal vectors? You will obtain 0. So this one is CE1, C EIK minus 2, IK minus 1, wedge product with IK. And if you continue calculations, you will obtain this exterior product. And the proof is finished because assuming these guys are linearly dependent, you will obtain linear dependence of these elements. Linearly independent in exterior algebra. Yes, that's all. So since the result provides you with elements which are linearly independent, then the things which you use to start these elements, they also were linearly independent. Well, now it's all. Thank you very much.